Good morning, everyone. It's me, Bikesh, and I'm currently studying at the last semester of my bachelor degree in civil engineering at Pulchowk campus. And first of all, I would like to thank NEAJ for this opportunity. And the topic of my presentation today is row housing in Nepal and their potentials to pounding. So, as we all know, pounding means collision of the adjacent building during any seismic activity due to the difference of time period and drift, or let's say out of phase vibration, which could lead to the severe damage in our structures. So the provision of adequate seismic gaps will be provided between the adjacent building in order to eliminate such effects and make our building design safer and economic. Uh, on 25th April in 2015, Gorkha earthquake struck in Nepal, especially damaging the central part of our country. And talking about the Kathmandu Valley, the basin amplification in the Kathmandu Valley resulted in the higher time period, which is around 4.5 seconds along east-west direction and 4.8 seconds around in north-south direction, especially damaging the tall building, or say high-rise building, which is around above 7 to 8 story tall. But due to having less number of high-rise building in Nepal, the instances of pounding damage were also few. So you can say that we are fortunate in that case. But what if large number of such buildings were constructed and a major earthquake struck? So that could be a serious issue. Due to that lower damage of the Gorkha earthquake, it has further bolstered the people's faith in ecosystem building practices. Here in figure, we can see that the row housing practices in Kathmandu Valley and even the newly construction building practice is not addressing that seismic gap provisions in their construction. So this may lead to the severe damage and the may lead to the major consequences that we should consider. So in order to know the effects, the major question arises here is, will these row houses with such building practices in Nepal be able to sustain such damage should other occur? So to know the effects, we have selected 4 major earthquakes across the globe, including Gorkha earthquake, which PGA level varies from 0.177 for Gorkha earthquake and around 0.833 for Kobe earthquake. By taking these 4 major earthquakes, we are doing non-linear time history analysis, and the results that we are obtaining from this will be presented in the further slides. So talking about the objectives, the major objectives is to assess the pounding effects, for which we are evaluating the variation of link force with the separation of building gaps, and we want to suggest the seismic gaps for zero pounding force for considered earthquakes. And the other objectives includes evaluation of the variation of seismic gaps requirement with different PGS levels of Gorkha earthquake, and observe the story shear amplification caused due to the Gorkha earthquake, and compare the case-specific seismic gap requirement obtained from the depths with the coral provision. So to achieve these objectives, the general methodology we followed is as shown here, and through the various literature review and also says site visit, we selected the typical building models that could best represent the building typology in the Kathmandu Valley, and we modeled the building in etaps. After modeling, we assigned the property such as material nonlinearity and hinges in the building, so that we could capture the real effect of the building structures, and we perform the nonlinear time history analysis. Then finally, the results in terms of the pounding force versus gap and shear amplifications are presented, which we will be discussing on further slides. Talking about the building representative models, in the figure here, we can see the 2 building models. The left one is named as B1 plan, which is of 5 story tall, and in the right side of the figure, we can see the building name as B2 plan, which is of 7 story tall. The story height is similar in both the buildings, which is 3 meter tall, and the building is model and designed in etaps, following the codal provision of IS code. So the general structural dimension of beam, column, and slab that are required to pass the building as per IS code is tabulated here. Moving on to the next slides, we have material characterizations, and we used concrete of grade M30, which is of Mender's uniaxial material model. And to capture the energy dissipation, so we use the Takeda hysteresis model for concrete. Similarly, steel rebars of 415 MPa is used with kinematic hysteresis model. And the frame element in model is used as a line element. Model is a line element, and sail or slab is plane element. And to capture the nonlinear effect of a building as a whole, we have assigned the fiber hinge model in the column of length 0.1 times the element length at both ends. Similarly, hinges were assigned in beam 2, and to simulate the pounding force effect, to simulate the pounding force between the adjacent building, the gap element is used as a non-linear gap element is used as a link element, which stiffness is for which stiffness calculation we refer to the paper of Masboom and Alama. And using these gap elements, we have simulated the pounding force between the adjacent buildings. Yes, and with these 4 time history graph of the 4 major earthquake, that's Gorkha, El Centro, Loma Prieta, and Kobe, we did the number of analysis of non-linear time history in these models, and the results of pounding force versus gap and other shear amplification factors we observed. So talking about the results, here in the graph we have presented the link force versus gap provided, for which we can see that for Gorkha earthquake, it's around the minimum gap is required is 40 mm between the 2 adjacent buildings that we have selected, and the maximum pounding force generated is around 1200 kilonewton, which is at the top story level. Similarly, for El Centro, it is around 80 mm gap, and the maximum force generated is around 3500 kilonewton. Similarly, for Loma Prieta and Kobe earthquake, which is of higher PGA earthquake, the maximum system pounding force generated was around 6500 kilonewton in both the earthquakes, with a minimum gap requirement of 250 mm in Loma Prieta and 300 mm in Kobe earthquake. So we can see that the requirement of gap ranges from 40 to 300 mm for the selected model for Gorkha and Kobe earthquake. Similarly, we have also scaled the PGAs of Gorkha earthquake that occurred in Nepal and compared it with the codal provisions that are provided in NBC and IS 1893, from which the codal provision suggests that the minimum of 200 mm gap, around 200 mm gap is required as per NBC, and around 250 mm gap is required as per IS code. But the analysis show that the around 40 mm gap will be sufficient for the Gorkha earthquake if the natural PG of 0.177 G has been used. And similarly, by using the scale PG of the 1 G, it's around 180 mm gap that is required. And talking about shear amplification factor for Gorkha earthquake, the shear has been amplified highly, that's around 6 to 7 times in Gorkha earthquake in case of pounding, where we have used gap of 20 mm, and in no pounding cases the shear is not so much in the story level. So we can say that due to the pounding, the shear in the adjacent story level has been amplified. And finally, talking about the conclusion and discussion, the codal provision, although suffices the seismic gap requirement for Gorkha and El Centro earthquake, but it seems that it is insufficient for other 2 earthquake, that's Loma Prieta and Kobe. So the major earthquake, that's a earthquake of higher PGS, will also be taken into consideration for the codal provisions. Similarly, if you look into the story shear, it has been significantly amplified by pounding, making it necessary to control. And to control the pounding between the adjacent level, if possible, we have to provide the sufficient seismic gaps. If not, then we have to consider the change the design parameter, like making the building more stiff, so that the demand for the seismic gap requirement is minimized. And through our study, we want to aware on the severity of the pounding damage that may result if the current rampant building practices continues. That means if row housing building practice continues, then that could lead to the severe damage in building structures. So we hope that the potential motivation towards similar studies on pounding in other settlements of Nepal and maintenance of vast existing building stocks. Although we have to try to capture all the real scenario, but we also lack in
remaining time 1 minute.
Some of the aspects are like soil structure interaction we have not taken into consideration, and similarly stiffness of infill wall has also not been considered in our study. So this could be considered as a limitation of our research. And finally, these are the general differences that we looked into. Thank you for listening. This is our team, and we have been working under Dr. Chiti sister. And lastly, we want to add to the scope of this work by developing a pounding damage index, also by developing a risk map for the Kathmandu Valley, let's say, so that by developing risk maps and risk map and pounding damage index, and we know that lots of work and studies are yet to be done. So any valuable suggestion on these topics are highly appreciated. So thank you. This was from my portion.
हजुर, थ्याङ्क यू प्रेजेन्टेसनको लागि। अब हामी फेरि